Okay, so welcome to the Reactive Deep Dive track. What we want to do is spend the first session here where we're going to present all four of us around different parts of what it means to build reactive applications. And after that, you can sort of think about questions that you want to ask. Interrupt us along the way, that's also cool. But we'll have a second session where we'll go in, we'll have a panel Q&A, and we'll take questions from the audience as well as we'll probably bicker and argue among ourselves for the fun of doing that. The point of this is we want to talk about what it means to build a reactive application. So I want to start off with kind of why now? Why are we talking about reactive applications right now? And there's a couple of interesting things that comes from. We're now in an era whereby we're building applications that are part of a channel, and that channel is the primary means by which people are doing business. It's the primary means by which we get to market. You can think of many customers are connecting into services that, like years ago, they go to a shop or they deal with something in 9 to 5. That is not the case anymore. We tend to be having applications that are up 365 days of the year, right round the clock, through holiday times. And it can be at all sorts of extremes, from it's just shopping through to social networks, to games, to finance, to healthcare. These things are starting to change. So this era that we're now coming into is where the web channel is quite often the primary channel by which people are doing business. That means things are very different. We don't like to come along to a website and it says, sorry, we're down for maintenance, or it's down all weekend as people are doing stuff. We need to be up and available all of the time. We've also seen a change in hardware, particularly over the last 5 to 10 years. The world of whereby we were writing software for a lot of uniprocessor systems, whereby every year to 18 months these things were doubling in speed, that's over. We're now finding that CPUs are getting faster, but at a very different rate from before. But more interestingly, they're getting much more cores on them, much more interesting things on the silicon. And this is an example of the latest Haswell EP server chips. This was just out a few weeks ago, and we're looking at 18 cores on a single socket. That's going to keep continuing. Within another few years, we're going to be getting 50, 100 cores plus per socket from normal mainstream processors. So that is fundamentally changing how we're programming. We need to take account of that. We also have this world whereby we're now deploying services into the cloud. That can be for simple things to begin with. I've seen people do it for like things like continuous integration, but primarily now it's becoming a main way of people doing business. And we need to do that efficiently. So at times when we're busy, we want to procure more servers. At times we're not so busy, let's have less servers so we don't have those sort of bills. It should be like our electricity at home. We should get billed for what we need, but our software needs to cope with that and how it works. Like another thing that's really driving this is how our IT infrastructure is working. It used to be that you go to your IT systems people, you ask for a new server, and you maybe got one in 4 to 6 months. This was really very poor service inside organizations. It is still happening today, but we need to get over that, and that's why things like the cloud is becoming successful. So people say, well, we've got private cloud. Well, unless your private cloud has an API where you can provision a server straight away, you don't really have a private cloud. All you've got is some internal infrastructure, and people are adding things to their CV and how they're working. We also have lots of interesting technologies that are out there. Like many people are building things in J2EE, Rails, Node, whatever it happens to be. There's a major problem with a lot of these is they are just not good enough for these applications that need to be running 24/7. They need to be able to tolerate node failures. They need to support hot upgrade. They need to be very responsive. This is a different world we're entering. And what we're starting to see over and over again is a lot of these patterns are being discovered or rediscovered. Some of the approaches we're going to talk about today are not new. We don't claim to have any invention here. A lot of this stuff has been done for a large number of years. So in the telecom space, people have been building systems that would be reactive systems for decades. They had to because of the uptime requirements they have to honor. Those sort of requirements are going elsewhere. I've been seeing this in gaming, in finance, and also for other domains whereby these things have to be up all the time. They have to be very fast. They have to be very scalable. As a result, they're all having similar patterns. These architectures are all having similar patterns in how they're designed and how they work. So we've got all these people sort of discovering this thing at the same time. And what we want to do is distill down what are some of the qualities of these systems we're seeing. And they're primarily very responsive. They're not slow and clunky like some of the applications we have been seeing. They're incredibly resilient. They can have nodes die all of the time and they still keep offering a service. In fact, if you look at a very large scale offering from most people, like take Netflix or Google or Amazon or any of these people, their systems are constantly in a state of being broken. Somewhere on their network, there is more than one node that is currently broken. They keep working. They keep servicing user requests. They don't give up whenever some part of their system is down. They keep working. They also are elastic in how they deal with it. So we're not just talking about the ability to scale up. Also, we're scaling down a lot. I've had clients whereby during a normal week, you could have run their service on a couple of laptops. You reach the weekend, they needed tens or hundreds of servers. On bank holiday weekends and some holiday weekends, they're looking at thousands of servers for how they work. You need to be able to scale up and scale down like that. You cannot be running with thousands of servers all of the time when they're not being utilized. These are quite common patterns that we're seeing work. But fundamentally under all of this, like, it's easy to make the argument, I want to have a system that's resilient, I want a system that's responsive, I want a system that's elastic. Well, do you know what? It's not easy to do that unless they're message driven. And this is where we're actually fundamentally having to change. We're going to go through a lot of the properties of what it means to build a message driven system that gives you a lot of these qualities. So what's in a name? Why reactive? And what we're looking at now? Well, you do it one way, it's a response to the current problem. The fact that these sorts of systems are now becoming common. It's not just something that's done in odd parts of finance or odd parts of healthcare or odd parts of telecom. It's exploding out of there. It's becoming very much mainstream in how we're dealing with it. We also believe in that we react to this in the same way that Agile reacts to stuff. Don't go for the inventing stuff before it's actually needed. This is kind of why this is appearing and why you do the minimal thing to get this right. A lot of these systems are incredibly simple when done well. You don't put extra stuff inside them. We've got a manifesto where we're trying to explain some of this. We're just trying to give a name to this common set of patterns that we're seeing and the common practices that are behind that. So to take off, one of the first qualities that we're interested in is our systems responsive. This is an area that I'm passionate about. Well, what do we mean by responsive is it has to behave in a quick, efficient manner and give the desired results for what is there. If we just take the name. We were having this joke earlier that actually if we start defining stuff in our industry, can we at least start with people reading the dictionary before they give a name to something? Because we've got so many things in our industry that are so misnamed. So it kind of makes a nice start. Well, what does it mean to be responsive? If we do not respond in a timely manner, bad stuff happens. It can be very simple stuff through to users get fed up, through losing lots of money, to the extremes of people dying. But we're all on different parts of the scale with this, and we have to design systems that meet our actual needs. But the one thing that is not good is if systems don't respond in the desired time that we need them to, they're not good. They fail to meet their desired needs. Now, I like to look at responsive systems in one of three ways. First of all, I want to start with the service itself and how it's deterministic, and then we'll go into talk about how service times impact the overall responsiveness of something and what we can do about going parallel. So when we want something to respond in a good way, first thing we start is what's our service that we're offering, and it needs to be deterministic. To be deterministic, it's the ordered algorithms that matter. So back to good old computer science theory, we need to look at our algorithms, work out for the given input that we're seeing, how long will it take to respond? What is the dominating factor in that? This is back to big O notation. So for n number of products or n number of customers or n number of whatever those things happen to be, we need to respond in a timely manner. And this comes back to basic algorithms, so knowing this stuff. And how do you know how your system goes? Well, you can do code analysis, and that's all really interesting, but a much more interesting way is to actually measure your systems. Don't just guess, you got to measure. A great way to measure a system is in a histogram. So every request that goes through your system, measure the response time and record that observation. Every single one. Don't sample because sampling hides so much. You can record in histograms incredibly cheaply now. We're talking tens of nanoseconds for some of the best histograms to record observations, and HDR histogram being a really good example of this. And so if I record a system, you end up with a chart that looks like this, where you've got a number of observations happening for a given time period, or a given response time that's there. We see a system here that is mostly responding in under 1 millisecond, but it's also responding further out. So we've got to avoid some of the terms that will confuse people. And the classic ones are the averages that people talk about. So mode on this is here. That's the most common occurrence. We also hear people talking about median. And the median is the middle of the entire range when you line everything up in order of units. Often we hear people talk about mean. This is the average. This is the one you really want to avoid because it's very unhelpful. Like looking at this graph, mean tells me nothing about the most common occurrence, and it tells me nothing about all of the outliers that are really significant in the behavior for this. So let's get used to measuring. Let's deal with things like this. And what starts becoming very clear when you're measuring a given service, you will start to see that certain processes and certain threads in your thing will hog a resource, mostly due to being synchronous. We've got to get over this synchronous mindset that we keep having when we hog resources. I'm using the pig because it's a Danish audience. I thought it might appeal that you understand. Especially on the way into Aarhus is a pretty strong symbol of that. So we've got our services. How do we then work out how it's going to respond? Well, mostly this comes down to utilization. Because if you overutilize any service or any resource, you start getting an interesting effect. You get this queuing effect that happens. So the more you utilize something, the higher the likelihood that it's already being used whenever you come to need it. So if something's underutilized, you turn up at it, there's nobody there. You can easily use it. If you're running at very high utilization, you turn up to use something, there's going to be other users of that waiting. And so designing a system, you want to keep it under sort of 60 to 70% utilization. Otherwise, you get really, really poor response time. So it's understanding some of the basic math behind this. This is a 100-year-old theory and so fundamental to us designing systems, yet most people aren't applying it. So start thinking about how we utilize our systems and make sure you keep the utilization relatively low. And one of the best ways to do that is having fast service times, because the faster your service time, the lower your utilization will be. And you do that by not hogging the resource and don't go synchronous. You can also control queue lengths. And if you control a queue length, you can upper bound your response time. So if your queue's full, you just reject any more inputs that come in, and you can keep to an SLF response time. People go, oh, but that means you're rejecting things. Well, look at the alternative. You can take the approach of, I'll let my queues fill, and then if they're full, I'll reject input and say politely to your users, sorry, we're busy, please come back later. The alternative is you take in requests, you let your queues grow unbounded, eventually you run out of memory, you crash. Everybody's in the system gets a bad level of service. You can't service anybody else coming in because you're crashed and you're going to be down for a while. It's not a good approach to have. Let's be professional about this. So coming on to the third and final point is we need to go parallel if we want to break stuff up. So if I can't make an individual task faster, I need to break it up. And to break it up, I then got to start worrying about two things. Many people will have heard of Amdahl's law, and that's about how we can speed up things by going parallel, but it is restricted by which component of the algorithm is serial. So if only 5% of your algorithm is serial, you still cannot get greater than a 20x speed up. Now remember I started off by saying how processors are changing, how we're getting so many cores? It is possible now to get multi-hundred core processors, and in the future it's going to go going further and further this way, so we have to build these things. But Amdahl is actually giving you the optimistic view of the world. Neil Gunther pointed out that in measuring real-world systems, that is very optimistic. And we must also take account of the coherence cost as well as the contention cost. So for the things that are competing, they need to be made coherent, so that data has to be shared. And as soon as you add in that coherence cost, it starts to dominate, and we can see here in the graph where the bottom line starts to tail off. So even if we throw more processors at it, it gets worse. So we have to look at our algorithms, we've got to know where they're contended, and we've got to look at the cost of that coherence. So what this comes down to basically in most of our designs is if you have shared mutable state, you're in trouble. In many ways, it is the crystal meth of programming. You find yourself going fast for a while, and then all of a sudden things start going really wrong as it gets really complicated and gets messed up. You become like these poor shells of people who basically lose their teeth and want to die after a while. So how do we deal with this? Well, we break down our work. We break it down into batches and we deal with it in pipelines, and there's loads of really great ways of doing that. And talk to us about this in the next section of the talk. We can sort of break this down and explain some of what's going on. Let's not bang on shared memory because it's a really, really bad way to go. The way I like to think about it is what's happened to our industry is I think we're at a fork point whereby we have far too many hipsters, but we really should be geeks. We should be back to applying computer science and understanding what's going on and stop just following the latest cool trends. We got to measure, and we measure, we find out what we need. We apply science. I think it's one of the greatest inventions of the human race is the scientific method. Because if you apply it to almost anything, you eventually start getting towards the right answer. We've got to start applying these great discoveries that we have. And before I leave you, I'll give you one thought. Synchronous RPC. I've been watching Breaking Bad recently, so you're getting lots of drug references. But it has become the crack cocaine of distributed programming. People are wanting to do it, but once you start it, you're screwed. You're hooked for life. You need to undo your brain around some of this stuff and start learning about things like message passing and going asynchronous, because you'll just be so liberated in the things that you can achieve. One of them being, you can much easier become resilient.
So in this setting of reactive systems, resilient is the second property or quality that's really interesting, and from my point of view, a more interesting one. Of course, there's not like a new completely unified religion or the new unified church of reactive programming. This is many different things, many different practices, niches coming together, kind of realizing the same sets of patterns. And we're not all, like Martin, doing high-frequency trading systems. But it turns out this notion of resilience is vastly more applicable, and vastly applicable in lots of different places. And resilient, if we just look it up in the dictionary here, I'll just read this out loud. Resilient is able to become strong, healthy, or successful again after something bad happens. Or able to return to an original shape after being pulled, stretched, bent, etc. So here you get the idea. This is very, very exact term for a system kind of coming back together after something bad happens or after the system is stressed or bent or whatnot. Basically coming back, recovering after some kind of fault or error or stressful situation. And that's the second property. I think it's really something that we're going to see a lot more demand for than we have right now. It's kind of like security. Security is obviously something that has been demand for, but with the last couple of years of issues and security and privacy, etc., security has become so much more important. The same thing with this, as we continue depending more and more on our IT systems as infrastructure. Like at Trifork, we do some healthcare systems that are pretty critical. They have to work around the clock. So there, the IT system, to some degree, is really very important to do what you do. So bad things happen. There's so many different kinds of bad things that can happen. If we look at back at the definition there, they can be broken. Computer stuff can be broken. Computers, memory disks, network routers, cables, etc. Things break. And anything that can possibly go wrong eventually does, especially if you do it for a long enough time or have many enough things going on at the same time, eventually one of these things will go wrong. Things are stretched or resources are overutilized. Memory, compute I/O load, storage capacity, congestion, these things are pretty obvious. And all kinds of unforeseen things happen. Things that you didn't think of when you wrote the program as the programmer. Input validation, configuration, blah, 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 or just plain bugs. And the thing is, you can't just expect to buy a magic framework like J2E or whatnot that will, if you just use this technology and write your little program in that world, all your problems are solved. The system, the framework, the hardware setup, whatever, will take care of it for you. This is like, just like with security, it has to be designed in. You have to think of it up front. It's really difficult to add security to a system after it's built. Likewise, it's very difficult to add resilience to a system after it's built. So the primary design pattern in this. So let's get back to what this is about. This is about people meeting with this, realizing that there's a shared set of design patterns around this. And the primary design pattern is this notion of bulkheads. In Danish, it's skot. So it's what splits. It's these vertical lines you see in a large ship here that make sure that if there's a fault in the hull, that water won't spread to the entire hull. Right? So these guys, I wasn't part of doing the original Reactive manifesto, and the original one at least had this diagram very much like this, which kind of reminds you of Titanic, right? Trouble on Titanic was that these bulkheads they weren't high enough. They didn't really isolate the section, so water started running over from one bulkhead to the next. So the reason why I came into this was, of course, I mentioned this healthcare stuff, and I've been doing a lot of Erlang. And the one revelation that comes out of working with Erlang is it really gives you a notion of isolation. And the primary thing I'd like you to walk away from here with is to build resilient systems, you need to build isolation into them so that you can have your system, parts of your system break independently. So this is like with houses or properties, location, location, location. The rules of resilience is really isolate, isolate, isolate. And frankly, we're not used to doing that. It's really something that has taken me some time to get used to. So, from Erlang perspective, Joe Armstrong, who's one of the creators of Erlang, says you need at least 2 computers to build a reliable system, namely one that can observe the other, that can observe each other and take over for each other. So I would think a better picture of a better way to look at this resilience in terms of ships would be something like this. You would have the unsinkable 1 and the unsinkable 2. 2 Titanics on the maiden journey, and you'd have 2 guys standing here looking, making sure, observing whether the other ship was still afloat, right? So this would be a much more resilient. I think this is the primary design pattern of resilience. They need at least 2, they need to observe each other, but we can get back to that discussion. I think we agree on the fact that isolation is really important. So maybe we could kind of amend the rule a bit and say we want to isolate, and make these faults observable. You need to have a way where when something bad happens, somebody else will notice it. So there's various sets of solutions in this space, but one important thing I see as a common thing is you make errors or faults first class. And you're very explicit about telling other people when something happens. To explicit observation or sending messages when things fail. So today in, say, Java, where you have one big heap of errors, if something goes wrong, that wrong could be completely entangled with a heap of Java objects that are already in a sorry state, so you don't really know what happened there, right? But you want to make faults observable. That's the second thing. Then there's we're used to these various notions or units of isolation. We have data centers. We have multiple data centers, so we can have failover to another data center. We have racks or clusters or machines as units of failure. So you can have, if one machine fails, you can have another one take over. In terms of software, which is the level below the line there, we're used to thinking of in terms of operating system processes being units of isolation. A nice and clean operating system process, a Unix process, has its own memory space. It can't kind of randomly ruin another system process running on the same operating system. But we're really not used to having isolation at a more fine-grained level than that. The software components, the stuff that we use to build software. And that's what Erlang, that's the kind of the tradition of Erlang, is to have software components that are also isolated, just like operating system processes are. And it's kind of, when you start working with this, you realize that actually it is true, this thing that software faults are actually transient. You know, just like when Microsoft Word hangs on your machine, you just restart it and move on with your life. And actually, the same strategy works surprisingly well at the software component level or the part of your application level. And you just have to see it and try it. I can't really make a much better argument than that, because it's something that doesn't feel natural when you hear it for the first time, but when you try it and look at it and see it in real life, software components can be restarted and you can actually get something meaningful out of it. In fact, most errors that happen in a software system are of this transient nature. So the thing you want to do to build a resilient system, I'll amend my rule set once again. You want to isolate it, you may want to make the faults observable, and you want to have a way to do clean restarts. So you can restart the components from a known state. And I think that's a place where you can, if you want to learn more about this, I think in terms of building software components that are isolated, having some kind of actor system or a microprocess system like Akka has it or like Erlang has it. I say the Erlang version is better because they're more isolated. You should go read about patterns in context of actor systems, right? So you have software components that are running together in the same virtual machine, and each of these components are properly encapsulated, just like we thought of objects, and all talked about objects should be encapsulating state, etc. 10, 20 years ago. With actors, you actually do that. You handle faults outside these, so you need to have a way. Actors provide a way to fail entirely, right? So you can reboot an actor. So instead of trying to repair some state, there's some exceptions happened and blah blah blah. Typically, in typical Erlang coding style, at least, you just don't deal with it. You just kind of restart the component, and in most cases, that actually works really nice. And then you can imagine once you have notion of restarting one component, sometimes to restart a component, you also need to restart a couple other components because they're dependent on this one. So there's strategies called supervising strategies for how to manage kind of the recursion over restarting components. So there's a whole toolbox of things surrounding resilience that are patterns that exist out there. Haven't really ever seen them assembled in a coherent fashion across different technologies. Descriptions of this tend to be surrounding a specific technology. But there's all kinds of things like these, right? Heartbeats, append-only file formats that let your data be useful even if your things crash in the middle. You can start up again. There's various notions of actors and microprocesses. This notion of component local resources. You have in Erlang, you can assign memory limits or compute limits to individual components within your application. As I said, supervisors. We've seen circuit breakers. None of this is new. But we're starting to see this being used across a wide range of things. So when you know your stuff is isolated, you can just keep calm and let it crash. And that's really a big relief. Okay, so we're moving on to the third quality, property, being elastic.
Hello. You still awake? Hey, awesome. All right, so elasticity. So what does elastic mean? Well, it means that something is capable of rate change or expansion or contraction or able to be changed. So it's kind of fluffy, but I think we sort of get the picture right. And what we're going to talk about is why this is important. So here's a quick outline just to make sure that we understand the order of stuff. And let's just get going. So why do we need to be elastic? So why would I want to do that? Well, I think first and foremost, the rules of the game has changed, right? We don't see the same kind of applications that we have done in the past. So just to sort of enforce what we've said before, we've seen that back in the 60s to 90s, we had single machines, right? Now we have clusters of machines. Like we have a lot of machines. But we don't also only have single core machines, but we have multi-core processors. So we sort of see how we sort of adding hardware. And, you know, back in the days, RAM was really expensive. You had to do a lot of optimization to make sure that everything fit into your memory. But now we can have, I have more RAM in my cell phone than I did in my computer like 10 years ago. And I don't even know what to use it for. We have expensive disk back in the past, like really expensive disk. And now disk is super cheap. So we can have a lot of disk. And we had slow networks, and now we have fast networks. So in the sort of before, we had few concurrent users. Perhaps you had a mainframe or your workstation, and you had like tens or hundreds of users, perhaps even in the thousands. But now you can have hundreds of thousands or even millions of users. If you're successful and you release some new app and it goes viral, you might even have tens of millions of users in a very short time. But now, that is something that we see. It's just happening all over. And also, having very little RAM and very, very expensive disks, it means that we couldn't really capture that much data either. We needed to be really careful. Like, do you really want to store this stuff? Like, are you sure? Like, it's going to cost you some. And now, we can essentially store everything that we want to store. We can store everything. Also, when something was slow in the past, it was slow in sort of the seconds or even like days. But now we have latencies that are really, really short. If a website is slow, and in which case slow means like less than a second, then people will move somewhere else. So how do we do this? Like, how do we get the elastic stuff going? Well, first we need scalability, but what is scalability? Like, do we really understand what scalability means? So one common misconception is the scalability versus performance thing. So scalability is about the relationship between your latency and throughput, or sort of your graph of latency and throughput as you increase your inputs. But performance is about how long of a time it takes to do a single item of that input. So these are separate things. So in the past, when we were talking about scaling up, it was more about if we buy a fatter box with the faster CPU that only had a single core, then we would get a faster program. Like we had a single-threaded program, and we just bought a faster CPU and insta-speed, right? Insta-speed. Sort of, that was the scaling up. We can just do that. But I think right now it's more about adding more cores to a machine. So a fatter machine is not a machine with a faster CPU, but it's one with more CPUs. So is that the same thing? Are the CPUs getting faster in terms of performance in raw, sort of this core can do that work? Not that much. So what is scale out? Scale out tends to be, all right, so let's just buy more machines. Let's just buy extra machines and make sure that our system can run on more machines. So if we look at it, if we have these sort of data centers with clusters of machines with machines in them and some sort of virtual machine, some node that's running there that has threads, that has CPUs, that has caches, and everything is sort of nested a machine within a machine within a machine within a machine, right? It's sort of like that. So if you think about it, buying a bigger machine with more cores is sort of the same thing as buying more machines, right? It's more cores, but they're just not in the same machine, but they are in another machine. Sort of the same thing. So what's interesting about scaling is not just we can buy infinite amounts of hardware and just run our system on all machines at once at all time, but it's about being able to contract and scaling down and just using the hardware that we need. Because if we can scale out, then theoretically we should be able to scale in as well. And this is about money. It's about not paying for stuff that you don't use right now. So how can we do this? So I think the first thing we need to do is that we need to be asynchronous. We need to de-shackle ourselves from the synchronous thinking. We need to have a boundary between components. And this sort of ties into the isolation part as well, because if we decouple two endpoints from each other, they can also be isolated. They don't have this tight coupling. And what we also need to do is that we just need to avoid blocking. We need to make sure that even if we're this is asynchronous, but now I'm going to block the current thread of execution until I get a reply, and I'm going to wait forever, because that tends to be what people do, is that they wait forever. What happens if that thing goes down, never replies, or somebody else needs to use your thread? You're just stuck there. It doesn't work. What we also need to do is we need to divide and conquer. We need to decouple our stuff. We need to take our problems and we need to sort of break them apart to see what can we do if we take the individual pieces. Can we run this there and this there and this there, or do we need to run them in one chunk? Perhaps we don't. We also can do something called pipelining, which is what Martin mentioned earlier, which is we can think about the flow of communication and transformations within our system and designing that flow. We think about so that input comes in here, it goes through some transformation, then goes out there and comes in over there and does some stuff. So if we can sort of take a step back and think about this, then it doesn't really matter if those stages of transformation live on the same machine or if that's just different functionality on multiple machines. So if we add more machines, then we should be able to execute parts of it on other machines. Also, we need to share nothing. We need to start having this shared mutable state addiction. We need to start thinking about individual components that are isolated. We can't reach into the brains of each other and read the thoughts and write thoughts into each other's brains. We need to start communicating instead. And what's really important to do that is something called location transparency. It means that the component that I am talking to, I don't want to have an assumption where that component exists. It shouldn't be hard-coded where that component lives. It should be an address so that I can send to it. And it doesn't matter if it currently lives on my machine or some other machine. Doesn't matter. And in order to sort of get the full picture, we need to obtain metrics. We need to understand what our system is doing. Because when we have metrics and when we start to see what's happening, we can also use that. We have information about the system itself. So that ties into the elastic part. So when we have these pieces, then we can do something called reactive elasticity. If we have metrics about what's currently happening within our system and we have a bit of a history of that, then we can sort of, okay, it looks like there's a lot of people coming in to buy stuff in the e-commerce store right now, so we better spin up some new machines to be able to handle that load. We can sort of react to the changes of our users or the behavior of our system. But it's fairly frequent that we can also do this in a predictive way. If we know that Black Friday is going to be one of those days where we typically need 10,000 times as many machines as we usually do, then perhaps it doesn't work to have reactive elasticity for that case, because it might just take too long to spin up 10,000 new machines. So perhaps we need to have a combination of both. So reactive elasticity can even out sort of unexpected tops and sort of the falling trends, right? So it can sort of smoothen things out. But predictive elasticity makes sure that we can stay responsive and we can sort of service the users while we're sort of heavily loaded. So in general, we just need to become elastic. So once we do, we can profit out of that. We don't need to pay for hardware that we're not using, and we can pay for hardware when we need it. So that ties into message-driven.
Hello, everyone. So, message-driven is sort of a way of tying all these different traits together and lets them sort of bring what they can to the system. And it's not really what message passing provides; it's actually what it makes harder or even impossible. Which is kind of an odd thing, right? We usually think that there is something great that something brings that makes it a better system. But in the case of passing messages, actually we take away some of the things that we're used to. We take away some tight coupling. It's sort of like this, right? If your personal space is violated and you want to get a little bit back, you intentionally put a boundary there, right? You basically push back a little bit. And that's actually, boundaries are good, right? So having that boundary sort of forces things. It's a little bit like this. This is a great book, Anti-Fragile. It basically talks about how systems, when they're stressed, they develop coping mechanisms, and those coping mechanisms are actually make for a stronger system. But you can also apply it in this case. It's really about forced decoupling and forced separation of concerns. When we think about messaging and we think about using networks to sort of separate components, or if we even think about going from process to process where they can't do anything shared, or if they have to orchestrate it so that they can share memory, things like that. What we really have is a binary boundary. There's a binary boundary where we can't just toss a very complex object across to something else. We have to serialize it in some way. That boundary of actually us hitting that boundary like that, or actually having the boundary where we have to think about that, and those things are more complex, actually makes us think about how we actually put those pieces together. It's also an asynchronous boundary. In other words, we can't just go and wait because it doesn't feel natural, right? How many of you are like web developers or UI developers? Or have done any web or UI development? Oh, great. So the idea of something that's asynchronous should be something that you're pretty familiar with, right? Things come in as events. You think about, somebody clicking a menu item and then going off. What happens if you're doing a UI and you initiate an action and the UI freezes? Well, that could be good. There may be things that you want to do that. But often you'd like to go off, do that, and then while that's being done, do something else. So that idea of asynchrony. It may shock you that, a lot of us actually interact with developers who are really used to doing things synchronously. Even things like accessing disk is a synchronous operation, but it doesn't have to be. It could be asynchronous. So when you actually force this decoupling and you force actually thinking about things in a more asynchronous manner, it actually does lend to lots of different designs. Very akin to this is event ordering and implied correlation. So as events kind of happen, the order which they can happen, especially among multiple different recipients, these are things that protocols deal with all the time. But we also see it with all kinds of different systems. Once you start actually having an asynchronous binary boundary in them, you have to start thinking about the order that happens, Ordering can happen where it's going to typically happen in this order, but it may not. It may happen in a slightly different order. And the more events you have and the more messages, the more ordering kind of takes over, and the correlation of those things. And the last thing is sort of errors of messages. They're really no different. So start thinking about the messages that are being used and using messaging to actually pass back errors and do that. Sometimes locally handling an error is the right way. Sometimes passing it along is a better way. So really, having these things separated by an asynchronous boundary basically facilitates these other traits, because what it does is it actually forces certain patterns on the system that can take advantage of elastic, make a system more responsive, and make it more resilient as well. Resiliency is a really key one here because when these things have an asynchronous binary boundary, they have an implied bulkhead between them, right? It's often really difficult to force in things that would, basically get over that bulkhead. So let's take these traits in turn and sort of see a little bit deeper about how they sort of they're bolstered by message-driven kind of approaches. Well, with responsive, asynchrony is built in, right? So now, the reason why UIs, are mostly asynchronous is this is how we have evolved from responsiveness. When we're interacting with a human, we want things to be responsive. We want constant feedback. And what we've seen is doing UI development has kind of evolved this way. It's not a coincidence. It's because this tends to work. Synchronous calls, if you think about the really bad UIs that you see that pause when you do something, right? We all would consider that to be an unresponsive UI. The term responsive actually has an implied meaning in UI. So, this is, very closely tied to it. Decoupling forces responsive design. It just does. So when things are more decoupled from one another, they're actually more responsive. And naturally, they just fall out. Amdahl's law in USL, which Martin mentioned, has a tremendous impact here. As things are more serialized, they will slow down. And that's only getting worse, and it will not get any better. In fact, it's going to make systems that now, seem to be pretty responsive as you just start pouring more cores in. If you're not thinking about things asynchronously, they're going to actually get slower than they are today, which is kind of a frightening concept. And that really gives you the idea that contention and coherence are actually evil, right? They're actually pretty bad. So you have to start thinking about not having intention, reducing the level of coherence that is required in systems. Resiliency is extremely important. I want to echo the Kresten's comments that we have systems now that have to be up 24/7 or else they impact business. 24/7, 365 is the norm with a lot of systems that have to deal with e-commerce. If you're not there for a customer when they come, they're going to go somewhere else. That's just what we expect as consumers. So even in retail space, resiliency is paramount. So boundaries and bulkheads go hand in hand. So forcing those things into place, often at a very fine-grained level, actually gives us more resilient systems. Supervisors and hierarchies, also work very well with message passing. So observing something is a lot easier when you can just listen to the traffic between them. An observer that can just sit and non-obtrusively look at the system and just look at the communication between it can tell if something is alive or not without having to actually be in the middle of the conversation. Also, when you have messages as a means of communication between components, live piecemeal upgrade becomes something which is possible. Erlang does this. It's not, totally easy, but no system really is when you have to think about upgrading in any real case. Also, localized errors versus passing errors around. These things become a lot easier and a lot more, and open up a world of possibilities when you think from a more of a messaging sort of orientation. Elastic. Decoupling is really key to scale, and Amdahl's law plays another really big role in here. And we can think of a lot of things like spin up, spin down, and in and out as, it becomes a lot easier when you think of it from a message passing perspective as opposed to, a shared mutable state perspective. And again, contention is the enemy here. Coherence is also extremely bad because you won't have something which is elastic when it has a lot of contention on state and when it has to have a lot of coherence to operate correctly. So, the shared nothing designs, everything else, these are central to that. And being able to separate these things via, passing of just binary blobs is actually very important. So just to sort of give you an idea of how we can take even traditional blocking operations and sort of decouple them. I thought this was, giving an idea of how different ways to do this. REST is actually reactive. A lot of times we think about REST as being, you send a request, you block, you wait for a response, right? Just think of it from the client side. But, if you break it down, HTTP has a request, it has a response, that's a message, that's a message, that's a message, and that's a message. And I'm using the term message here very, very loosely, right? Because, from this perspective, you can also think of the request and response as, the normal messages. But I'm thinking actually these are messages. These events that happen within this sequence are messages. You can even break it down into those kind of slots. And you can do a lot of stuff while you're waiting, from originally sending that request to getting that response back. But you have a couple things to think about. And I've taught for many years, and as I have taught, I've asked students, to sort of, do things like this, where they take something that's blocking and then make it more asynchronous in nature. And one of the things that typically happens is the blocking that happens here is usually because of correlation. You want to send a request and you want the response, and you want those two things to be correlated. So when you break them apart and you make them asynchronous, how do you actually do correlation? That's a real thing that is something that people struggle with. So don't I need to wait to do that? Well, the answer is no, I don't obviously need to. How can I do this? Well, if I assign, say, an ID, a number, put it into, say, a map, I then send my request. It lives for a time. When a response comes back, I just look it up, and now I have my correlation. Simple as that, right? That's one way of doing it. There's many different ways of doing things like this. And again, none of this is new. This is actually, a long time ago, we decided that there should be a lot of web services standards. So, and I'm seriously meaning a lot of these. If you want to actually take a look at that wiki page, it's surprising how many web services standards we have. And a lot of times what they do, a lot of them do this independently, is they try to break the synchronous nature into asynchronous. And the way that we've done this traditionally is like this, with a synchronous request and a synchronous response. And together, they're kind of request response async, but not totally. But as close as we could normally get it without sort of going into the protocol HTTP and changing some things. In this case, the protocol holds us back from going there all the whole way. Sort of give you an idea, we could keep going on about different types of things, and just wanted to seed some questions and things for this. But there's a lot of mistakes that protocol developers have done over the years. Not me, I'm always perfect, but that's very rare. And there's a lot of best current practices, things that have actually done really well. So I just wanted to give you a smattering of things to think about. Generating new errors on error reception. Like if you're going to talk about sending errors as messages, think about this sequence. You receive an error from someone, and you generate an error and send it back. And then they generate another error and send it back to you. Does this ever stop? Potentially not. So you have to think about, what the sequence of, do you handle errors and how you handle errors, and do you generate certain types of traffic? A good one on the good side is TCP reset. TCP reset is like a get out of jail free card for a TCP connection. It just basically resets it, gets rid of it, and aborts it. That actually is really easy because now anything that doesn't fit can cause it to abort. It's a very simple rule. Things like that, where you think about what's the default behavior and how do I get out of this really, really quick? It goes back to more of a, sort of failing fast kind of technique. State machines. State machines are actually great. They're nice and simple and concise, and they actually make things a lot simpler to follow. Strict ordering requirements. This is one that always trips up protocol developers. I'll ask just a simple question. What happens when you have a response in HTTP before you send a request? Ordering may be important, right? It's allowed. We can talk a little bit more later. That's one that Martin has pointed out to me. But there's others from a lot of other protocols. Sometimes protocol developers do assume a certain order when they shouldn't. So, again, not going to judge on it yet. So, I think with that, we'll take a little bit of a break, and we'll come back, see what questions you guys have. We'll talk a bit, and we'll see you in a bit.
Just to get it started, I would like to to ask you again about what your superpowers are. I think it's about time you share your superpowers with the audience. So my official superpower is I'm very good at making people shut up, which is why I got this role today, because it's extremely difficult to make Kresten shut up. But I found a way of not even making him coming here. So let's move to Martin. What's your official superpower?
Well, besides being scared of you. put on the spot to be asked this. Well, at university, I had a bit of a party trick that I was known for, and that was to pick up a large glass of beer with my teeth and down it in one go. It got me into all sorts of trouble.
I've asked Kresten to fetch a beer. What about you, Todd?
I fill an aircraft seat very well.
That's
Maybe a little bit too well.
Viktor?
All right, so what's my superpower? I'm the master of bad analogies. That is my superpower. It's deadly.
Thank you very much. So if anybody wants to share superpowers, you can also use the app for that. But I think the floor is open. You must have some questions from the last hour to give to the panel. Okay, Eric. What do they disagree about?
Where is Kresten?
You must disagree about something.
Oh, I know exactly what we disagree about.
All right.
Because every developer disagrees on this naming.
Naming is hard. I think tabs versus spaces. Do we have somebody who prefers spaces here? Look, I'm a space guy. Agree on that?
Oh, Emacs versus VI. Oh, yeah. Emacs.
Ed.
Yeah, I think one of the things that will... I think one of the things that many people will disagree about is how you do things like resilience, because it's usually how you combine it with other things. So, like, we can have fun and we can make fun of the ACA folk here for a bit, but it's not really fair in so much. But like, you can have excellent resilient models, but you often trade things off. So I would disagree with the supervisor model, for example. I think it is a workable solution, but I also think it's one that doesn't work when you need to be responsive. Because when things start to go wrong, it can take too long to realize, and the going up through a hierarchy to make a decision, just like bureaucracy in an organization, I think it's an example of how humans apply bureaucracy in software. It's Conway's law in action. I think there are better ways of achieving resilience without supervisor hierarchies.
I'm just going to step back for a moment.
I don't know this guy. I think we're onto something. I think it depends on what you're optimizing for. So the more you're willing to optimize for some specific trait, the more you might end up sacrificing or optimizing away for other stuff. So perfect fault tolerance can be hard to achieve, but if that is what you need to do, if you're sending something to another planet, for instance, you might have to trade away responsiveness because you can't really communicate with that satellite thing that's way out there. So I think it's how you sort of place yourself in the graph of these traits for specific implementations or specific systems.
Yeah, I would challenge the view around it that the model that's for resilience, though it does work, it's very much rooted in humans trying to be intelligent, and I think there's a danger in that. If you look to nature, nature doesn't try to apply intelligence to be resilient or successful or adaptable. Complex adaptive systems show us that in other ways, like multiple ways of doing the same thing and picking the first to succeed are often a much more successful strategy, and a strategy that survives many more failure modes, including the failure mode of your bureaucracy system.
Okay.
Okay. Started.
Sorry, I'm running at 100% utilization, so there's some latencies every now and then. Yeah, I'm not always responsive.
Maybe we should take another question that you actually hear, Kresten.
I'll grab the next
question
yeah.
from the gentleman in the blue there.
Yeah, I would like to hear, are there any examples, like some open source projects or anything that uses some of those principles you've been talking about?
Yeah, actually,
question.
Actually, this is a question I also got from several people walking out of here. You know, it was a nice presentation you guys did. Nobody could disagree with that. I mean, tell us something. What should we do?
Are they here?
I don't know. I'm not certain. Maybe some of them are. Some of them are not. And of course, there's stuff you can do. There's that question, and then there's the question. So you're talking about all this messaging. Does that mean we should just use message queues or message queuing everywhere? That's another question I got in the break here. But let's take the first one. Of course, you can all go and write your stuff in Erlang, and that's the right way to do it right now. Right? And you're laughing.
You're not biased, right?
I'm a bit biased. Well, I grew up as an object head, right? I've been programming Java for 15 years, 20 years, or something like that, and realized I needed to learn something new. I mean, that's this kind of thing. I think Erlang is kind of like what Smalltalk was to OO in many ways. Probably, Smalltalk was the first, or one of the first really successful OO languages that gained widespread adoption. And many of the things in OO were designed either in Smalltalk or in Simula, of Scandinavia, of course. And even though those two weren't in themselves successful in terms of number of deployments, etc., the people that learned these things back when they went to school or took the time to learn them later on, they could use that experience to be successful in so many other ways and apply the patterns that you learned from there in so many other things. So you see the big C++ frameworks were written by guys who did Smalltalk first. So in so many different ways, there's actually a lot you can do by just read a book about Erlang. Or read a book about Akka, which is Typesafe's attempt to copy Erlang into Java land, right?
You mean attempt to bring it into the next millennia?
Well,
Well, actually, what Kresten said leads very well up to a question that I got over the app, and that is, how do I get further resources on the topic? Now, you just said read a book about Erlang, but are there other places that people can go to find resources here?
Yeah, absolutely. I think there's tons of resources out there, but it's a really good question. So I think there's both the getting some experience, like getting your hands dirty and try stuff out, which is one approach, which if that is your approach, I mean, downloading Akka or downloading Erlang or downloading something else that has these sort of thoughts built into them makes a whole lot of sense. But I would like to complement also having the books, but also looking at the history. And as Kresten said, I mean, object-orientedness and the actor model, which is sort of what underpins both Erlang and Akka, is in essence very much the core of object orientation. It's about objects that communicate by sending messages. And that's how Smalltalk was originally intended to be implemented, but given the hardware requirements back then, it was not feasible. So they had to sort of opt out of that. So it's an old model. It's from 73. There's been a lot of papers written on it, but there's also books both on Erlang, on Akka, and also in sort of general message-driven software books that are useful. And also a lot of conference talks. I've done probably 20 Akka talks the past years. Kresten's probably done a lot of Erlang talks. There's probably tons of other Erlang and Akka talks and other technologies that might be more suitable to consume for you guys. So.
Yeah, I guess kind of Erlang and Akka are some of the poster childs that are out there that people know of, but there's also other great work that's been around. The early work on Tandem Nonstop by Jim Gray and Pat Helen covered a lot of this, and that sort of work went forward. I don't think you actually need big frameworks to do a lot of this, and this is what is kind of odd, is we're now in this world, we think we need big frameworks to do everything. Replicated state machines, if you look at the research on that, it describes a lot of what you need to do as an alternative. And those ways are good. They're one way of doing it. There's also other ways. And I think replicated state machines is a really good example of this. So if you just write your plain business logic in a language using no libraries at all, just basic data structures, and write your business logic, you put a queue in front of that, and I mean an in-memory process queue, really simple, and a queue coming out of it. Okay, you've got some interesting problems now. Well, how do I make this persistent? Well, just a persistent log. There are tools out there that will let you do that. You can replicate that to more than one place, and then you can run those. So you can start building this up from really simple primitives. We just are not thinking that way. We've been conditioned to think you need a great big J2E container. Where's the product that lets me do this? It does raise questions like, okay, how do I do hot upgrade? Well, you're sending messages around. Those messages need to be versioned. You need to support message extension on that. So you always add fields, you never take fields away. You start to learn these things over time as you work in the area. I think that there is good work out there. It's hard to get it all together in one place, I think, is the slight difficulty that we have at the moment.
So this is all very much convergent, right? So it's happening these years, right? Getting into the mainstream. And I think that there's a lot of interest in microservices, which is also very much related to this, because these microservices naturally have APIs or versioned messages or whatnot in front of them. So that's another aspect of it that also kind of leans this way, I would say. Microservices, that's another hot topic that everybody is doing. I don't know, if we look into the future, there might be a next generation programming language that kind of takes all these great ideas and is more modern than Erlang and doesn't have this actorness tacked onto the side like we have in Akka, but actually has processes as first class. I could very well see that happen. I mean, we have Dart is trying to do that, at least. I don't think they got it exactly right, but it's Go. Well, Go is another contender in that space, right? They have a shared memory system. There's like a mutable shared state, basic assumption. But that's also a step in the right direction. And there's what's it called? Mozilla's Rust, is I think very interesting.
Yeah, and I think I would like to add as well, like, while I agree that you can handle all of these things yourselves, which I have done, I think you find it that it's very common to see that you're repeating yourself when it comes to the application of these things. So all the patterns for fan-in operations, like you're accepting multiple streams of messages and you need to do something with them, or the inverse where you're sending out to multiple recipients, they tend to be very, very, they're few, but they tend to be really reusable. So there's a lot of value in not having frameworks, but really having toolboxes where you can opt in to the tools that make sense for this specific task. Tying back to like the circuit breaker pattern, where you don't want to handle it yourself perhaps, but want to have it as a tool in your toolbox. And also, if you go having an Erlang system that communicates with an Akka system that communicates with some tandem system from the 80s or something, it's the same kind of problems that we're solving. It's communication. It's about coordination and making sure that the flow of information stays as it should. So these different systems are going to have the same kinds of primitives built in to deal with these things because they are fundamental problems. So it's the toolbox approach, I think, is very, very fitting in this case because it means that you can opt into what kinds of stuff that you need.
I think, we learn by actually trying things. I know that myself, if I want to learn a new language, I actually have something that I actually write in the language and, see how it fits. And that's the same thing I've done for, 15, 20 years, to really learn a language. It's a non-trivial exercise. I actually write a small little mail server. It has a lot of different aspects to it. This year I did it in Go. It took me, a little bit longer than an afternoon, but not too much longer. So actually try something. If you are struggling with something where you're looking at, say, a refactor, and you're like, wow, I'd really like to separate these two things. Actually try to separate them. Put one on one server, one on another, connect them with a TCP connection. Work through that. See what you get. I mean, you're going to learn more by looking at that and trying to find solutions for it than you're going to probably learn, in just sort of reading through, other things that are written. By doing that, you'll probably encounter all kinds of edges and all kinds of different ways of doing it. In that simple thought exercise, even if you don't actually carry it through or even use it, you may find that there's some interesting things that you've had to think about by doing it.
Okay, thank you. I think we'll need to take some questions from the audience because the Danes are unstoppable today. So first we have Helena.
question about the virtualization, because Martin, you said earlier that building reactive application, you don't use virtualization, but aren't there any some kind of high performance virtual images or Windows creating virtual machine that you can use, or is it abandoned completely using virtualization?
Okay, so the question is, can you apply virtualization to reactive applications? I say yes, you absolutely can, but you have to be aware of the consequences and what you're dealing with. So for example, whenever you're setting up a virtual machine, how you connect that to a network really matters for your responsiveness. Now, if you're not dealing with high throughput and low latency, it's not such an issue. If you're purely dealing with resilience and elasticity, that's probably fine. But if your load is going up significantly, or you just want to be efficient, these things start to matter. What's nice is our virtual machines now are greatly improving. We went through the era of having the likes of Xen, which is a very inefficient virtualization system. We then went into KVM, which was a big step forward, much better. But now we're getting to things like containers, like LXC and Docker. It's getting much more efficient now. And so we're getting the ability to have really nice lightweight, but also good quality containers. But we still we need that ability to configure the I/O particularly. But that's the same in a native world. It just is an extra step. We're too often having the problem whereby people write to disk or write to network and they're just unaware of what they're doing. They're not configuring buffer sizes correctly. They're not configuring the routes through their operating system efficiently. And we just need the responsibility of knowing that and setting up. And it's not a huge job. It's just something we abdicate too often.
But I guess that applies as well to all kinds of virtual machines. Especially, you get sort of an aggregate effect if you're running a virtual machine within a virtualized operating system on some virtualized hardware on some virtualized planet. I don't know. It aggregates, right? So being aware of both the settings and configuration that applies to achieve the goals that sort of are important for that specific system. I think that's a sort of general advice.
Mm-hmm.
Yeah.
We got another question from the gentleman over there.
What's the difference between toolbox and framework?
Yeah.
For me, framework is just way of collecting tools.
Yeah,
it's a good question. So I'll take a stab and let me see what the other guys say. So framework for me is something that sets the frame of your application. It's something that you work within. And toolbox for me is something that you opt into when you need it. So if you always have to live inside the frame, no matter if you need it or use it, that's your framework. That's the thing that exists around you. So that's my personal definition. I'm not sure what the other guys say.
Yeah, exists around you, you being the program, of course, that you're writing, right? I mean, I'm imagining, I'm the little guy.
Not physically.
You know? You have that...
Not physically.
No, but, you know, don't you have that feeling when you're programming? I'm sitting inside that program I'm writing, and I imagine I'm pulling levers around. So when you do that, and it's all around you, then it's a framework. But if there's something you can opt in, and you can have multiple of these. Typically, you can only have one framework, but you can have multiple libraries or stuff like that. Toolboxes, yeah.
Okay, thank you. We got another one.
Yeah, I have been here for a long time, and
well, the question is, where are the boundaries between these things? Is it where are they, and what's the difference between the levels of the operating system and the application level? I think the answer to this lies in that what happens when you start programming in this way is you end up thinking a lot about protocols, right? Protocols become very important. And it's something we're not used to thinking that much about as programmers. So there's a whole discipline of protocol design, thinking in terms of actually sending data, not objects. You're sending information that needs to get flattened and get reenacted on the other side or whatnot. So so there's a lot of practices and experiences that we haven't really talked that much about, but they come kind of out of this being forced to write protocols, right? So Todd talked about this some, right? Mm-hmm. So when you're forced to do that, and that's kind of one of the core ideas, you start thinking, in many different levels, you start thinking differently, right? Todd mentioned a few, but just the fact that having things be flattened, you need to have correlation IDs explicitly between there's a message coming in and I need to know what the response is. You end up thinking about things going two-way. We're used to, from the OO and the old RPC-ish world, we're used to these calling in and getting a reply. Things are they're like functions that have a return value, right? So we use the same abstraction across the network, but when you go to protocols, you suddenly realize that it's a two-way street. You don't just have an interface, a set of actions that you can call on a remote site. It's actually, there's a conversation going on. And so the notion of protocol is like a two-way interface. And almost, if you take a Java interface or C# interface, that's a one-way thing, right? You call it. With a protocol, you need to have a notion of a conversation, right? It's like a formal description of what is the kinds of conversations we can have here. And I think that's a very profound thing that we haven't really talked that much about. And I only have this vague feeling of this really changes something significantly.
It does change a number of things. I think the OSI model is interesting. So you got for those who don't know, there's 7 layers in the OSI model, and it's everything from the media that you deal with the networking right up to your application stack. If anyone was in my talk earlier, one of the things I ranted a little bit about is how we use abstraction and how we misuse abstraction. Because as Dijkstra very well pointed out, abstraction is about being precise. It's not about hiding, it's not about being vague. You add a layer of abstraction to be more precise. So if you take the OSI model, if anybody's programmed in the financial space, you use a protocol called FIX, Financial Instruments Exchange Protocol. They've conflated different layers of this. So what this is basic good design. You should have separation of concerns at any given layer, and you don't conflate concerns together because it causes problems. So one of the things that they did within the FIX model is they've got a sequencing protocol within their interaction. It should be at layer 5. It should be session only. They made this available at layer 7, but they also didn't make it properly available. So what happens is you've got session level layer 5 things incrementing sequence counters that you need to know at layer 7. And as a result, you cannot make a resilient system because you cannot detect loss and deal with it at the upper layer 7. This is design. This is really basic good design. Like getting back to the basics of designing protocols, separation of concern, knowing how these things work. And I think once you start getting into ASYNC things, so people ask about virtualization, like is the operating system a library? Like one of the fundamental things with how we deal with operating systems is they're synchronous APIs. This is one of our performance issues. So imagine you have an asynchronous API into an operating system, like I'm sending packets to a network and then I'm getting responses. I'm not send, block. That's what's slowing us down. We should just be able to send, and then get responses of what's actually been achieved. And that's how we start getting things together. That's the protocol. And protocols go way beyond just even messages, APIs. Like you deal with a file system. You open a file, you do multiple reads or write, and then you close a file. That is a protocol of interaction. Many people, when they design their APIs, don't document their protocol. That's actually way more interesting than the API itself. So I think it's one of the fundamental things, and I've had the pleasure of working Todd for a while, and he pretty much only does protocols. But it's great to see that that's a normal way of thinking. It should be standard for us. Instead, we're just too busy learning the latest version of AngularJS or whatever it happens to be. But just fluff. It's fluff because it'll be gone tomorrow. Like, how many people can design a good protocol? How many people really know what separation of concerns means? How do we decouple stuff? What's cohesive? The things that stay with you for life in this industry.
Still, it's a good idea to go to the AngularJS presentation tomorrow. I'm sorry, I just have to intrude with some questions. So we have a lot of questions.
Yeah.
So, and there's some in the app, and I know there's also somebody waiting in the audience, but I'll just remember the app as well. If processes should be allowed to crash on a bad message, are there any good patterns to avoid crashing repeatedly on the same message or similar messages?
Sorry, I've dealt with this as a messaging vendor for 15 years. Poison messages. typically what happens in a lot of guaranteed messaging systems is a poison message causes an infinite replay. I'll give you an example. You receive a message, you crash, but you never acknowledged it. So when you come back up, you read that same message. You then crash. You then start back up, you read that same message. You then crash. The way that these things are dealt with is usually human intervention. I wish that I was joking. People have done all kinds of different things to try to avoid poison messages, such as you try too many times and then you give up. The best way that I have seen to actually deal with this is actually to have the system understand that you have tried this so many times, I'm not going to let you try it again. The app sometimes has to get out of the way and be made to get out of the way. So it's a difficult one, but the best thing I've seen is actually don't let the app process it. Have something else which can tell when this is happening, usually by observation, and actually forbidding the application from processing it. And then let a human after that intervene and figure out what to do.
Yeah, I would add the app approach to that is I think you do that at a network level, but the mistake is how most people do error handling. They litter their code with exception handlers and then it becomes difficult. I think you do two things. You deal with errors locally if you can. If you don't, you let them go right to the top. And then you deal with them and you move state forward. So I like to have a very top level error handler. And if something's a poison message, you mark it and you move on. You make sure the top level can move on your state and keep going. If you've got stuff in between, it's usually very difficult to make the right decision. And yet you see people have the catching exceptions, doing stuff, ignoring them. It's usually a smell. I like to see an exception handler right at the point of where you deal with it or at the very top level. If there's anything in between, you really got to question why.
So I'd like to add another angle on this question too, because in Erlang land, or the idiom from Erlang, not because it's Erlang, you typically create a new isolated session or something like that for every new user, every client. Every TCP connection has its own process that isolates your interaction with that client. So because processes are so lightweight, you could just create a new isolated process for every socket, and then the processing goes on there. So the Erlang way to handle this would just be you have this poison message would crash the process. The client would lose its socket connection and would have to retry. Right, so that doesn't poison the rest of the system. That would be a typical practical way of doing this in Erlang.
Yeah, I think we do sort of the same thing in Akka as well. I mean, it's about delegating risky operations to where they can fail safely. I would also not recommend to reprocess messages that are poisonous because they're poisonous. So it's better to just send them somewhere else where they can be either stored for later analysis or just dropping them and just going on with life. So I think those are the...
Okay, thank you. Now we have a question again from the gentleman in dark blue.
I'd like to hear, I know that a lot of the stuff you're talking about messaging and message-driven systems are something that Wolf and Hope also have written a lot of things about, but I was wondering, why does it come back? It's something that we have that we've had in a lot of years. Why is it relevant now again?
I think that when we talk actually up here about messaging, we're actually talking about many different things. We're not just talking about something like JMS or MQ or queuing or even shared memory. We're actually talking about all kinds of communication mechanisms, with the basic communication mechanism being a blob of data that's sent from one point to another. It could be over shared memory. It could be over the network. It could be over all kinds of different things. So when we're kind of using messaging in a little different way when we talk, because there's so many broad options for how things communicate. Like how Akka actually communicates internally is actually different than how Erlang communicates internally. And what things like that Martin and I are very familiar with in terms of shared memory, lock-free data structures, lock-free and wait-free data structures is very different than those. So we sort of have, use message and message driven or message passing as sort of an overarching term, but you're not limited. Anything and another thing that kind of occurred to me while sort of putting together a couple of the slides was anything that provides an asynchronous binary barrier is actually kind of messaging. So anything that gives you that, it provides that. In other words, or it forces you into that, but it also, anything that provides that kind of fills the same thing. But
just to jump in, so the new thing here, I think, I read as the underlying current in this is that we're also now promoting in-process messaging, right? So the way you construct a program that you normally think of as running in one JVM, for instance, right? You also think of the way that components inside a single JVM talk together. That would also be by means of messaging. So I think bringing it down to that level, I think that's maybe what's not obvious in our first presentation. Is actually that's the thing we all have in common is we actually want to push messaging and all the nice patterns that Gregor Hopi and all kinds of other people have promoted all the way into the application. So it's part of it.
Yeah, I think Viktor mentioned this, and there's another thing we haven't mentioned so far, but also shows this is CSP, communicating sequential processes, with the likes of Go is based upon. I started out programming transputers, and not having shared memory is a great thing to get used to. You communicate by passing messages. You build your own local state. Like Viktor says, like we don't go reach into each other's heads. Like, I could ask you your name. That's sending you a message to find out. I could also go over and crack open your skull, find the neurons that represent your name, and do that. But actually, when we share data, we so often do that in shared memory or via databases. It's a very unclean way of doing it, and it's not scalable. Whereas if you just send a message, you build your own model of the state. We've all got our own representation of the world, and we do that by stimulus going in and out. We design systems like that, it scales up much better.
Are you ready for another question? There's one in the app. How do these concepts work with concepts like CQRS and event sourcing? You remember what CQRS is?
Yeah, I'll take that. So command query responsibility segregation. So this is really nice. There's one thing I like is to be able to serialize an incoming set of messages, events. So this is the whole thing. What's the difference between a message and an event? Well, an event is something that happens at an instant in time. A message is a way of transmitting that. So actually, I think messages are more interesting because you can transmit all sorts of interesting things inside messages. Events are one of those things. But let's say events are just things that are happening in the world. They're a stimulus that's coming in. They're all coming in as messages. We serialize that stream of messages. From there, we can rebuild whatever state we want. This is the view of the world that we can all have. And so by doing that, I can build a view of the world. And if I take that into a primary node, wherever that happens to be, I can mutate that, I can build that model up. I can then send that to lots of other nodes because you can have one or more nodes being the central truth for mutation, but then others are just all lagging that, building another copy of the model. You can then query that in any sort of way. This fits very well with that sort of model. Now, there is a lot of confusion around what is event sourcing versus event driven versus whatever. I think it comes down fundamentally two things. You either take pure events, messages, whatever you call them, in, and from that you build a model. And that model then is built as a set of deltas from that, and so you've done that. The other way some people talk about is what you store is the actual mutation data itself, and from there you change the model rather than build it on that. I would caution people slightly if you're going into building resilient systems that there is not so much research done on the idea of storing the deltas up front. Because all of the work on resilience, you go back to what Pat Halland and Jim Gray and all have done, is you store the incoming events, you keep the state machine, and that way you can rebuild the same results. That's distributed state machines. The other approach is you do the mutations and you save the delta afterwards. That's what databases do. There is a current wave on the web of people saying, well, I'll save what will actually change as an event. Now, it's working in most cases, but it has nowhere near the analysis and research done on it for building highly resilient systems that those other two have. It's a bit like build your own security. You don't just invent this stuff and it sort of works most of the time. You want to do stuff that's been peer reviewed, well understood, and then it's much more safe and resilient.
Anybody else in the panel want to say something about CQRS and events also?
Probably better to just try to get through the questions. I could speak about this for hours.
The trouble is, we gotten through the questions.
That's good. That's good. Then we can.
Well, we are between them and beer, but are there any questions from the audience? Who wants beer? Okay, right, there's one there.
What about eventual consistency and the user's point of view? So you're talking about asynchronicity, and we have to make sure that the users get a response at the time, but maybe you have some running process that takes too long to end. What do you do then?
Personally, I like to break down any long-running task into a set of small tasks that are all bounded on time, and the great way to deal with users is give them constant progress updates. Keeps them happy.
I also think that it plays into the sort of event sourcing model. Actually, I come at this in a little different way. I look at ordering and time as not being, things are always strictly ordered. Eventual consistency actually makes much more sense to me than any other type of, transactional update. So to me, a state has one other index to it, time. So state is bounded by time. I think actually that as humans, we actually understand this. At a certain point, if you query a system and you ask them for the status, we usually think of the latest status. But and to different people, that may mean a different time. But if you attach time to it, like a database read, where you actually say what's the value of number of followers at a particular time, that makes much more sense. And so I think by adding something like time to it, you naturally make it so it's unambiguous, and and you get rid of some of the hairiness that is around consistency in that case. So I mean, and that maybe that's just the way I kind of view it, but I think it makes it cleaner.
Yeah, for some reason we've warped our minds into thinking that the entire world can be synchronized all the time, right? So lots of these frameworks we've seen over the last 20 years have tried to hide any kind of inconsistency. So we've gotten used to this worldview where everything should be consistent. But I think it's much more natural. I completely agree. So if you think of things in operations in terms of sending letters to other people and responding to them, if you have a catalog of things you can buy, that this catalog was printed some time ago. So maybe by the time I order, the prices have changed or whatnot. There's lots of these kind of, if you think of interactions with other systems in terms of these physical things, which it really is, then I think we truly believe it. We understand it naturally in many ways. You just have to kind of undo. We've been in it's like another drug, right?
Yeah.
I don't know what kind of drug. I'm not that much into.
Well, there's a lot that mess with time.
Yeah, there's a lot that
Chloroform. I don't know.
It's the LSD of being in sync, right?
I would just like to add to that, because I think that's important. So if you have, let's imagine that you have a warehouse and you deal with shipping things in and out. So you have this system that's perfectly transactional ACID, completely consistent at all time. And you do an inventory of your warehouse, and then you see that somebody's stolen 50 of something in there. What's the system of truth? Reality or your perfectly consistent database?
There's actually a question from the audience now.
Before you was talking about the conversation between the two corporations of processes, and you have the analogy of a catalog. I would call it multicasting messages to a lot of processes. Where do you see that kind of protocol in this in application today? It's not often used, but it could be saving a lot of resources and so on and so on.
Multicast or selective broadcast or something brings in a whole different set of things. And we have a lot of experience in actually how protocols work on top of things like multicast or broadcast. One thing that you don't have to worry too much about with sort of just one-to-one or point-to-point communication is ordering. So, for example, you send one message to a recipient, you send a second one. They usually, pretty much are going to arrive one after the other. But if you're sending out to 100 different receivers and you send 2 different messages in the general internet with something like multicast, they can be in any order at different receivers. So that adds a whole different level of dimension. I like to think of it this way. Unless you enforce ordering, it's going to be random for those. So there's a lot of different things. In fact, there might be something that Martin and I are doing around this that we've been working on recently. But, I've actually been doing multicast protocols. It's how I actually started getting into protocols, reliable broadcast, reliable multicast. And maybe that's why I'm so twisted in certain ways, thinking about ordering, thinking about those kind of things at that level. But yeah, there's a lot of different efficiencies that can be received. In fact, some interesting work was just done last week. It's starting in the next IETF. There's a birds of a feather session on a way of doing explicit multicast in the general internet that's kind of unique. I'd like to see how that progresses. Some really interesting work. So it's not dead. It keeps popping up here and there. Things keep progressing. We'll see. It's a great tool. It's just it adds a few more dimensions of things that are a little bit tricky.
Yeah, it is tricky to deal with, right? I mean, it's typically used within like clustering software or discovery software or as part of atomic broadcast mechanisms. So there's a lot of usage of it, but it's tricky to deal with. So it's in system software.
It depends on which domain. Depending on which domain you're in. For example, it's very heavily used in finance. When you're sending out things like market data, you send it out from a source to many different gateways, which then send on to customers. And so it tends to be a more high-end commercial product. So what Todd alluded to is we've been collaborating on an open source project to bring a message transport, talking of OSI model. It will be out there as a full layer 4 implementation that will be available, and it will do unicast and multicast, and it will be very fast and very high throughput. So good low latency, good throughput. We'll do unicast and we'll do multicast. So there will be something that people can start using.
We have time for one last question before beer, and I found one in the first part of this panel. Do I have to teach my Java developers Erlang to be responsive? I'm looking for best practices, tools, libraries for Java developers. And I don't know, do you want to make a round robin on that, where we start with Viktor? And if you can make an answer which is tweetable in 140 characters, that would be great for the audience.
Oh, wow. Well,
no pressure.
No.
Brilliant.
I think that, no. So let me clarify. I think as a Java developer, I think it's important that one does not have to learn a complete new language and a complete new platform and a complete new paradigm of doing something at the same time, because it tends to create this huge threshold or barrier to entry. So what's good about this case is that Akka is written in Scala, the Scala programming language, but it has a Java API as well. So if you want to just take things for a spin and try it out and sort of work the reactive angle, I think that's a very good starting point. It's not in 140 characters, though.
But thank you anyway, Viktor. Kresten, 140 characters.
If I was forced onto the JVM platform, of course you could also program Erlang in Erlang. Well, that aside, if you were forced onto the JVM platform in real life, I would rather program in the likes of Closure or some such that actually enforces the discipline of proper isolation. And I think that's a more important aspect, actually, in many ways. Than it's a thing that's more important to learn early than getting used to. So I would opt for a language that has some notion of isolation properly, and that's a good thing to learn. It has so much value.
Thank you. Let's move on to Martin.
Okay, well, as someone who writes a lot of Java and helps a lot of Java users, you do need to reprogram their brains a little bit. They've been brain damaged mostly by J2EE and various other frameworks that are out there. But once you get over it, it's amazing. Like, one of the things I find quite useful is to build prototypes with people. And it's amazing how so many of those prototypes have made it into production and totally superseded the system that's there before, being built in a fraction of the time. To give you a good quote, I can't use the full language because it's probably too colourful to be recorded, but a person who's become a very good friend of mine worked with me at LMAX and some other previous companies, and then he moved on to do some other things, and I got a call from him one night, and he called me a B and various other names, and what he was saying is, "You have me broken. I cannot work anywhere else again." Having gone to working that way, he liked it so much, he could not go back to working on J2E apps and other things like that. Because it actually is, it's so fast. It's not just the fact these things are resilient, elastic, scalable, all those sorts of things responsive. They're so fast to develop code in. That's the big win. And it's easy to reason about the code, it's easy to deal with it. And people just churn stuff out, and the business like you more afterwards because it redefines a new relationship with them. Because you're taking out all of the things that were in the way. In many ways, it's about stripping things back rather than adding things. And I find it's worked well.
Thank you. 114, a different number system from Martin and Todd.
No pressure. I actually think that programming languages are like instruments. I agree with Rich Hickey on this point. Programming languages are like instruments. We get very comfortable with a certain instrument, but to really expand a musician's portfolio and what they can do and how they think about music, they actually take on other instruments. They take on other challenges, other media, right? So I think actually we should perhaps think about letting, developers pick the language that they'd like to do. If they'd like to do a system in Python, that's perfectly great. And by separating these, the components of a system and breaking them apart, we actually can do that a lot easier. So if I had to tweet it, I'd say I think programming languages should be considered more like instruments, and we should consider ourselves more like musicians and try different instruments and expand our repertoire and not be afraid of it.
In a tweet?
Thank you very much.
That's close to 140 characters. Come on!
Well, I think there's one more question, but we have to take that over beer. And honestly, since the question is what about .NET, it's probably best to take it over beer. So thank you very much to the panel.